And so the problem is the graph, our quiz problem, the graph, this function, it reads x minus 5, x plus 3 times x minus 2. So what do we do when we see something like this? We find the intercept. Find the intercepts and gotta let y equals 0, which will give us the x-intercepts, or x equals 0, which will give us the y-intercept. Y-intercept is really easy, just plug in 0. But we'll do that. Okay, so y equals 0 means this equals 0. And for this to equal 0, and I really would like to see this written out like so, this, or this. Okay, because sometimes these are more complicated formulas here. You have to set equal to 0, and you got to know it's this or this or this. I think you know that. And you did find the zeros correctly, but to do it formally, we want to do this. So I'm just going to put 3 dots here. We add 5 to both sides, and you get x equals 5. And the whole point of the dots is whatever we get here, that's an equation we have to solve. And sometimes it's harder to solve than just x minus 5 equals 0. So I have to understand we're solving an equation here. And the solution, any solution to any one of these equations will give you y equals 0. Because it makes one of these things 0. Okay, or x equals -3, or x equals 2. At this point, we can begin to start over. Now, I always like vertical lines, dotted lines, to indicate x coordinates. So the biggest coordinate we have is 5. So I'm going to put x equals 5 out there. And then that determines the scale for everything else. X equals 2. Well, 2 is a little less than half of 5. So x equals 2 could be represented right here. And we don't want it over here. We don't want it over here. We don't want it exactly halfway between 0 and 5, but somewhere just a little left of halfway. Gives us a reasonable picture, okay? And we're just doing, hand-drawn graph. We're not trying to be meticulously accurate, but we're trying to be reasonably accurate. Okay, and then x equals x equals -3. Well, -3 is a little bigger than -2, so x equals -3 maybe goes about here. Now, if I measure these things and see if they're all in the right proportion, it ain't going to be so, but it might be fairly close. Okay, reasonably. Okay, now. X equals 0 implies y equals 0 minus 5 times 0 plus 3 times 0 minus 2 equals, that's a 5, and the 5 looks like a 3, don't do that. Okay, and that's -30, no, that's +30. So we've got 2 negatives and a positive, okay? Now, I noticed somebody out there got -30, they punched it into your calculator. So you gotta be careful how you punch it in, and then check out your signs. Got a negative, a positive, and a negative. Okay, has to be positive. So we have the y-intercept. Now, instead of trying to put the y-intercept, which is at 30, on the same scale as the x, as you might do, especially if you have some sort of graph paper that you're using, okay? 30 would go up here, 5, 10, 15, 20, 25, 30. I can almost not reach that high. There's no reason for that. When you're graphing polynomials, it's very frequent that you could have your zeros, your x-intercepts, between -10 and 10, and you get a y-intercept in the thousands. Okay, that's not in the thousands this time, it's 30, but 30 is big enough. So I'm just gonna say, okay, I'm gonna put y equals 30 here. So my y scale is different than my x scale, but there ain't no way it could be otherwise for most polynomials. Most polynomials will give you pretty big y-intercept, or the y-intercept won't be on the same scale as your x-intercepts. Okay, now I didn't show you the whole picture there because I wasn't careful about what put the board. But again, we see that there's x equals 5 and 2, which was visible. You can see the x equals -3 there. We understand that -3 is somewhere between but well, that's 3 units. That's somewhere between 2 units and 5 units. It's reasonably accurate. So now I know I have this point, this point, this point, and this point. Why this point? Because if x equals 0, y equals 30, and right there is where x equals 0 and y equals 30. I've got to go through all these points. Now, how do I go through these points? Well, I can make this up a little picture here. See, there are a lot of ways I can get through these points. Okay. It's not very well to scale. I can do this. Okay. But no, I can't, because the only way I can go through the x-axis is if x has one of these values. If x has any value other than these three, then none of these are going to be 0. So you're not going to get 0. Okay, so no. Okay. Another thing is, if this is supposed to have come up here and just touched this 0, that's not going to happen. That can only happen if you have an odd power or an even power of x minus 5. So if you had x minus 5 squared, then it could hit this thing like a parabola. If you had x minus 5 to the fourth, x to the fourth gives you a shape that's kind of like a parabola, but it's flatter near the origin, as we've talked about. So that's not going to happen. Okay. Another way, you might try to draw it. Go through these points. Maybe. Okay. Well, again, that's fine, except here. This is your point corresponding to x plus 3. That's where we got the -3. And x plus 3 is just to the first power. So it can't behave like a parabola at that point. Okay? Does that make sense? So the axis of these points, I don't have room to write out the reason, but the reason again is because none of these factors is 0 at those points. The only place they're 0 is at this point, or this point. If none of them is 0, they aren't going to give you 0. Okay, I've said that twice, but it's what we're saying. And x minus 5 isn't raised to even power at this point. And the only way it's going to behave like a parabola or a higher power our even power is if that is raised to the power, okay? So another way to say it is locally, in the vicinity of this point, the graph is pretty close to a straight line. Like this would be, or this would be. Now, it doesn't look like it's close to a straight line here because it's curving, but if you zoom in really, really close, then you see that it is pretty much a straight line. Just like you don't see the earth being curved, even though it is, because you're so close to it. You get really close to this point, it looks like a straight line, same at this point. It has to be the same at this point, like here. Now, this isn't right because gotta figure out how to hold this chalk. Bothering your knuckle, it's not fingering. Okay, at this point, uh, x plus 3. Oh, it's written kind of small, but that's what I'm saying. So that can't be. Okay, so these are all flawed. Now, how are we going to do this? The other thing is the end behavior isn't right. Okay. So let's just talk about end behavior. As x goes to plus infinity, so does x minus 5, x plus 3, and x minus 2. In other words, if x is a really big positive number, then subtracting 5 from a really big positive number leaves you a really big positive number. Okay. Here, adding 3 to a really big positive number's still positive. Big positive. Okay. And same here. Okay. So the product of these three numbers goes to positive infinity. So your end behavior here isn't right. So this graph couldn't. Okay. Now the end behavior over here would be okay. As x goes to infinity, this could go to infinity, right? So I note my end behavior. It's like this on the right hand. Now on the left hand, as x goes to negative infinity, each of these will go to negative infinity, right? So you'd be multiplying three big negative numbers and you get a big negative number. So I can come down here. Infinity's hard to write low on the board. I've got to work on a way to avoid having to do that. Okay, all these go to negative infinity. So their product, x plus 3 times x minus 2 times x minus 5 it gets a, if you multiply three big humongous negative numbers, you're gonna get a really super humongous negative number here. Okay? So that's at the left end. That means at this end, small there, you can't really read it, but you know that means end behavior, okay? Now, with these end behaviors and the fact that you can't turn around at one of these zeros, and the fact that you can't go through the x-axis except here, here, and here, can you sketch that graph? Okay, so now we're gonna draw the curve, and you did a good job of that. Let's just do it for everybody. Okay, so we gotta start low and go through this point. And then we have to go through this point because we can't go through the x-axis between here and here. So we gotta come up here, we gotta go through this point. Now, actually, what's probably gonna happen is we're gonna come up here. It's not really gonna peak at this point. There's no reason it should. It might, but it's unlikely. So don't be afraid to make it peak where you think it ought to peak. If it peaks here and then comes down like so, maybe turns around and comes back up like this. Okay? Now you don't know how low to go here. You don't know how to go high here, how high to go here. Okay? You learn that in calculus, and it's actually pretty easy once you learn a little bit of calculus. I could show you how to do it right now. It's that easy, but you know, whether you learn calculus, if you have calculus in your future, okay? If not, then this is sufficient. But you know, this point and this point here, the high point and the low point, you know there's a high point over here, between here and here, somewhere between these two. And you know there's a low point here between these two. You don't know how low to go. You don't know exactly what the x coordinate would be, like the x coordinate of a vertex quadratic function. You don't know that. You don't know this. Again, with just a very pretty modest a bit of calculus, you can find these out pretty easily if you need them. Some of you need in calculus, some of you don't probably in your curriculum. Those who do would appreciate this. All right. Well, that's that. Now let's see what happens if we change this function a little bit. Okay. So now I'm going to say let's function looks very similar. Matter of fact, use this whole board here. So here's the original statement of my quiz, but I'm going to put a square on this one, and I'm going to put a. What does that change? Doesn't change the intercepts at all. Okay, all that changes is the way the function behaves at the x-intercept, at some of the x-intercepts, so that your graph is going to, and it's very possibly going to change your end behavior as well. So graph is going to have the same x-intercept at x equals -3, at x equals 5, and at x equals 2. Here, here, and here. You got to find your y-intercept. Okay? Find your y-intercept and then figure out your end behavior. So I'll let you think of that for a few minutes. First, find the y-intercept. original graph. See if you can. You don't need to do this. You don't need to find the x-intercepts. That's going to be the same. Okay, but you do need to find the long run behavior and the y-intercept. Okay, now determining the end behavior and then determining the behavior at the zeros. Okay, there's a lot of detail involved in it. Okay, so we've got to make sure we understand all these details. Excuse me a second. Let a better piece of talk. Okay, now devil's in the details here, but you remember that here I determined what happens as x goes to plus infinity, right? Well, as x goes to plus infinity, you can pretty much see that every term here is going to go to plus infinity. They're all going to be positive, so that it should be pretty obvious that we go to plus infinity. Okay, so let's say every factor goes to plus infinity. Okay, so y goes to plus infinity with attitude, because you're going to have a square of something that gets really big, which is going to get really huge. This is going to get really big, and this is going to get really humongously huge because you're cubing it. Okay, so this whole thing is going to get very big very fast. So it's going to go up very fast after you hit x equals 5. Okay, and I say really fast, I didn't write off why, but you understand, because we have so many infinite terms or terms that approach infinity being multiplied together. Okay, now the way you want to work, as x approaches negative infinity, x minus 5 approaches negative infinity. Now you have x minus 5 cubed. If you cube a negative number, well, if you square a negative number times a negative number is positive. If you cube it, you multiply it by itself again, and it makes it negative, right? So if you cube negative 3 times negative 3 is 9. Multiply that by negative 3, you get negative 27. Does that make sense? Okay, so x minus 5 cubed has to go to negative infinity. And again, it's just because of signs. You're cubing it, meaning you're multiplying 3 negatives. That's got to give you a negative. Okay. X plus 3 goes to negative infinity. X minus 2 approaches negative infinity. So x minus 2 squared approaches positive infinity. F of x is a product of two factors that approach negative infinity, right? One factor that approaches positive infinity. We can write it out. This approaches infinity. This approaches negative infinity. This approaches positive infinity. So y approaches positive infinity, and that's a reason really fast with a little bit shorter space there. Okay. Well, we also have to find the y-intercept. So what's the y-intercept? Well, the y-intercept So you just plug 0 in for x, and you do the arithmetic, and you find that y equals 300. So we sketch a little line here and label it y equals 300. Now we can connect the points. How do we go through x equals -3? Well, that's just like y equals x plus 3, which is just a straight line, right? And so x plus 3 is linear. And these things don't change much in the vicinity of x equals -3. So we know we go through here and we go straight through this point. Whoops, something's wrong here. Right. Uh-oh, I squared this. This ought to be times -8 instead of times 4. So this ought to be -600. Okay. So when I drew y equals 300 here, because I was careless there, I saw a 2 and I didn't really look at that 3, even though I knew what it was. Okay. So my graph wasn't going to work. If I come down through this, I can't turn around and come back through this point because I'd have to go through the x-axis. And I can't go through the x-axis except at these 3 points. So I better modify my graph and put my y equals -600 here. So let me pretend I never made that mistake. But you see that if you make a mistake in one of these steps, your graph isn't going to work. Okay. the graph wasn't going to work if my y-intercept was up here. Okay, so I've got to come down through this point, and then I've got to go through this point and then come back up here. We're going to do that something like this. Okay, now at x equals 2, well, that 0 came from x minus 2 cubed, right? So it's got to go through this point like a cubic function. So it's going to come up here, and it's going to flatten out before it starts to go back up. Okay, and that's the way your cubic function works. And then we're going to hit the 0 at x equals 5. Like x minus 5 squared, that's quadratic. That's like a parabola. So it's going to come up here, but it's going to turn around, and then it's going to go back up. Okay, makes sense? So here it's near to 0, it acts like x minus 2 cubed. That doesn't really act like x minus 2 cubed because you have these other numbers here. And when x is equal to 3, you have like 8 here and you have 1 here. So it's like it's like 8x cubed. It's a vertically stretched x minus 2 cubed. I don't want to write out like vertically stretched. That says stretched, although you can't read it. Okay, that's the word there. It's like a stretched x minus 2 cubed. Okay. And it could be reflected. It could be an upside down x minus 2 cubed. It came down here, it could go through like this. Okay. At this point, near 5, 0, it's like stretched x minus 5 squared, which would be the 12. Okay. And I'll say if x was 5, you'd have 8 here, and you'd have 3 cubed here, 27. 8 times 27 is 226. So be vertically stretched by a factor of 226. You're pretty steep parabola. Okay. So let's list behavior at the zeros. Here we have a good explanation of this. It's a multiple of x minus 5 squared. Y equals x squared. Horizontally shifted plus 5 units. If you horizontally shift the squaring function 5 units, you move it 5 units to the right, and it's got a vertex right here. Okay. It's stretched, and it could be reflected. In this case, it's not reflected, but it is stretched. So you just want to understand that it's stretched. Okay. There is zero. Like a multiple of x minus 2 cubed, which is y equals x cubed shifted plus 2 units. Okay. So that's basically what you're going to need to know. Graphs of factored polynomial. Okay. Now there's another thing. It's actually easier to sort out than this, but it still takes a little bit of practice and a little getting used to. So I'm going to go back to this original function. And I'm going to multiply these two out using the distributive law. Okay. So I'm going to do all the stuff in gory detail. That's x minus 5. Then I multiply this by what? X times x minus 2 plus 3 times x minus 2. This times this plus this times this. And that's x minus 5 times x squared minus 2x plus 3x minus 6. And that's easy. Just x times x gives me x squared, x times negative 2 is negative 2x, 3 times x is 3x, and 3 times negative 2 is negative 6. That's how I put it there. Okay. So that's x minus 5 times x squared plus x minus 6. Now I got to multiply that up. That's x times x squared plus x minus 6. 5 times x squared plus x minus 6. And that equals x times x squared is x cubed. X times x is x squared. X times negative 6 is negative 6x. Negative 5 times x squared is negative 5x squared. Negative 5 times x is negative 5x. And negative 5 times negative 6 is plus 3. Put all that together, we've got x cubed. We've got an x squared and a minus 5x squared, which gives us minus 4x squared. We've got a negative 6x and a negative 5x, which is negative 11x. And we got plus. Okay. Now, f of x divided by x plus 3, we know is, well, here's f of x. And we know we can divide this x plus 3 by this x plus 3. And let's just write it out just to make sure. It's the same as x plus 3 over x plus 3 multiplied by x minus 5 times x minus 2 over 1. Why is it equal to that? Well, because if you multiply the numerator by the numerator, you get the same three things. If you multiply the denominator by the denominator, you just get x plus 3. But this is just 1. So it should be clear that this is x minus 5 times x minus 2. Okay? And x minus 5 times x minus 2 is x squared minus 7x plus 10. I didn't do all the steps of the distributive law, but you probably do that in your head. Okay? Now, what if you didn't know that this thing here factors like this? What if you were given this and asked to factor it? Say, you want to factor 11x plus 30 given that f of negative 3 equals 0. So here's your f of x function, and you're given that f of negative 3 equals 0. Okay? Say if f of negative 3 equals 0, that x minus negative 3, which is equal to x plus 3, divides f of x without any remainder. Okay? Now we know it's going to divide without remainder if I did all this right. And we'll see whether I did all this right. Okay? But we're going to divide this expression by x plus 3. Uh-oh. Okay. And we know that this should equal this, so the result should be x squared minus 7x plus 10 with no remainder. But we're pretending we don't know this, and we're going to discover this. So we use long division. We write that out as x plus 3 divided into x cubed minus 4x squared minus 11x plus 30. Out here, but that's how we're going to write it out. And what we should get up here, we should get x squared minus 7x plus 10. But don't we? We should get this because if I multiply this by this, I should get this. Okay. So all that aside, let's just look at this mechanics of dividing this by this. Okay. Now, you probably don't have a clue how to start, probably never seen this before. Okay, so let's just ask a question, pause in a minute and talk about it. You divide x into x cubed, what do you get? And don't tell me yet. Okay, now, we did okay with this, but people are pretty rusty often with how to multiply exponents, okay? For example, x squared times x cubed means what? X times x multiplied by x times x times x, right? Which is x times x times x times x times x, which is x to the fifth. So x squared times x cubed equals x to the 2 plus 3, which equals x to the fifth, right? So with that, well, let me just ask a question. By x cubed to get x to the seventh. Can you show me with your fingers what power we use? Yep. By x to the fourth. Okay. Now, what would we multiply by x to get x cubed? Well, I think we see it. You have to, x is like x to the first power. You multiply by x squared, right? And down here, let's just check that out. X squared times x. Without using rules, let's just write it out. That's x times x times x, which is x times x times x, which is x cubed. Okay, so we can check that out. So x squared times x gives us x cubed. And then, of course, we've got to do x squared times 3. Okay, x squared times 3 is 3x squared, so we add 3x squared here, okay? So here's the algorithm starting to develop. Okay, well, you know, if you remember long division from 5th grade, that you subtract whatever you have here from what you have here. Okay, whether you remember that or not, that's what you do. Okay, I'll explain that more probably in class or in this class a little bit later on. So I'm going to put a little negative sign here and a little negative sign here to remind me that I got to subtract this from the x cubed, and I've got to subtract this from the negative 4x squared. So that x cubed minus x cubed, of course, gives us 0. And then negative 4x squared and negative 3x squared is negative 7x squared. Okay. Now, I generally don't bother writing down the 0. I just make sure that the signs are right and that when I do this and this, I get 0. So this is what I want now. Well, now, what do I multiply x by to get negative 7x squared? Can you write that down for me? Okay. So what would I multiply by this to get this? Well, I would multiply by negative 7x. So that negative 7x times x gives me negative 7x squared. And then negative 7x times 3 is negative 21x. Now, what do I do with that negative 21x? Well, I'm going to subtract it from the negative 11x. Okay? Now, to make that easier, I just bring down a negative 11x here, so I'm seeing directly what I'm subtracting. Okay? But if I subtract negative 7x, that means I actually add 7x. So that negative 7x squared, it should be saying x squared. Now I've got plus. I have to multiply x by to get 10x. Might better be 10, right? So I say, okay, multiply now by 10, and that gives me 10x. And then I multiply the 10 by 3, and I get plus 30. Now, I know I'm going to subtract these, so I'm going to put a little negative here and negative here. Okay. And I'll put my 30 here, but now I've got a negative 10x and the negative 30 to add to a 10x and a 30, which gives me 0. So I'm just going to double underline there to show it comes out with a. Here's the if for one reason or find it by one means or another. If we know that x equals 3, negative 3, gives us 0 here. We know that f of negative 3 is 0, then we know we can divide f of x by x minus negative 3, which is x plus 3, and we get this. So now we can write x squared minus 4, this thing equals this product, because this equals this times this. Factor this into x minus 2 times x minus 5 is the original fund. Okay? Okay.